let's continue. Let me open the table of content first. Okay. We are still on chapter 20 here. Still on homework simulation section. Let me open that. Okay. Yeah, we are still in this section, homework simulation. Patching multi-level translate.py. Yeah, checking out this Python script. Let me open that. I think this one, right? And previously we already having some improvement, I guess. Like for example here, this one, we are able to at least understand, I guess, how to get the page table entry, on which page the page table entry is. But yeah, I'm still not sure about this one. How to get the value from this page, I guess. In small table, okay. Yeah. I guess this one. How do we get this value? Hexadecimal. $1,724. This one. So how do we translate that? Is there any kind of information from this page, I guess? Wait a minute. Translate, okay. Speed. Okay. Press 53. index egg. I think from this one, the index. Okay. Index egg. It is this one, P5, right? Found it, and then yeah, bits 53, but then how to translate that? Okay, virtual address. Okay, this one we get the offset, I guess. So maybe there is no information. I mean, let me try. What is the offset again? Okay, this one. $28. I think page bit is 5 because of the assumption in the readme here. 32 byte, right? Something like this. So this is the page speed. Okay. Return physical address. Okay. Get value. I mean, I'm not sure if we can get the value here. Let me check. Wait, be right back. Okay. Can we really find the value here? Using the address, you can find the value that the memory reference is looking for. I'm not sure how we can get the value. Yeah. Well, maybe we can do something like this. Offset 28, right? And then the offset here. Okay. Like this. Maybe we only need to get. Oh, sorry. Maybe we only need to get until the physical address. Maybe. Yeah, maybe something like this. Let's check with this one. With the virtual address 3DA8. Okay. Paste, what is it? Paste directory entry. Okay. Maybe I should put this in the information here. Maybe. Okay, this is the index. Maybe something like that. This is to get the index. Is the index here? Is anyone curious? This is the max that we are using, basically to get the first 5-bit or the left most 5-bit, the binary digit. Yeah, something like this. Okay. Wait. 5. Okay, 5. Look like this is 15. Okay. Yeah, this one. Oh. Wait a minute. Let me try. Is this invalid? receive 10 bit. Okay, I guess that's from the 10 bit is from this one. So we have 15 bit virtual address with 5 bit as the offset and the rest as the virtual page number. Okay. 15 index 15. Okay, I assume this one, the D6 here. D6 width is 214. Is it valid or not? I mean, if we take a look at this, right? Yeah, something like this, right? And if we write shift by 7, it will become something like this. Basically, we only get the one representation here. If this is 1, then it is valid. And if it is 0, I guess that is invalid. Okay, there is that. This 6. And well, I think I can show you these two. Right. This is the marks that we use. To get this number or binary digit, I mean. Okay. Okay. Alright. So this is also valid. I'm kind of curious. Is there any invalid one? If I remember correctly, this will result in fault, page fault or something like that. But maybe this one, page table entry not valid, maybe. Okay. Finally, page. Okay. To get the page there. And this one is D6. Okay, page X6. Page X6. Guess this one. Or maybe let's do this. And then get the index X6. Get page table entry. Max here. Okay. this one. Okay. Is there any effect when I change the order? I assume there is. Okay, interesting. Maybe not. Okay. Yeah, I'm kind of curious if there is any effect when we are doing the n bitwise operation here. There, if we swapping, I guess. At first I assume it may be different, but maybe it is not. Yeah, I'm still not sure. Okay. Anyway, this is the this is, I think, valid. And well, think by 36, maybe 8. Oh, 5. Okay. 13, okay. This is, I guess, the bits. Or the index, okay. Index 13. Okay. This is 0, 1, and then 2, and then 3, and then 4, then 5, 6, 7, 8, 9, 10, okay, 11, 12, 13. So this one. What is it again? PTA, okay. 7F. Is it valid or not? Yes, similar to this one, I guess. 7F. Okay. Now we got invalid here. Let me check. Okay. I mean, alright. Right, okay. It is 0. So this one is invalid. Hello. Super. I'm currently learning about operating system. Reading this book, Operating System 3 Easy Piece. You can take a look at the description, or well, I guess I will copy that in the chat. Yeah, I'm trying to learn about operating system and currently trying to understand this paging concept, basically about the virtual memory management, and now checking out the homebox simulation here. This homebox simulation, taking a look at the Python script for the paging multi-level simulation. Yeah, trying to understand how this simulation works. Something like that. Okay. So this one is invalid. Okay. Now let's try another one, I guess. Or like this one. Paste directory entry, okay. Paste directory entry max. It is, I guess 10. Oh, yeah, this one. I mean the SIF. The SIF is the 10. So this one is okay. Maybe I can make the variable here. Maybe to make things a little bit easier. Okay. Save, okay. Alright. Okay, so looks like this is index 5 from the page here. Page, what is it called? Page directory, page register. Index 5. I guess this one. So this is the page directory entry D4. Okay, and then and 12. Okay, 12 D4. Right. Guess this is the, what should I call this? It's not really the PTA max. Maybe PTA valid max, something like that. And then PTA valid safe. Oh wait. Okay, maybe something like that. And then valid safe, okay. D4. Valid or not? Okay, it looks like this is valid. And now what should I call this? Maybe PFN max, something like that. I think D4, right? F, okay. Page XD4. Okay. Let me add another max in here. Valid max. Save. FN max. Let's change this first. The valid max. Okay. And then this one. PFN max. Valid save. Max. Maybe something like this. No, okay. Alright. FN max. No, yes. Okay, no. No, no. Yes, okay. And then 5 here. Let me check. Okay. Stable entry. I think it is in the in this one. Okay, page speed, right? Page 5. Page speed. Okay. Oh, right. The second here. What is it called? The second virtual address here is invalid. Okay. Should I put this something like this? The indentation, to make it easier to check the virtual address. Okay. Alright, page 48. means I guess this is the best table entry, right? And then this one is 44 4. Yeah, we can also do this. Okay, and then what is it called again? Yeah, this is getting the index from the page, I guess. Okay. Are you making real-time operating system? No, not yet, at least. Okay. Oh, bro, you're super smart. Keep it up. I mean, I'm not sure if I am smart. Well, I'm just trying to understand this, like how this, what is it called? How this simulation works. And yeah, it is a complicated simulation, I guess. Like there's a lot of stuff going on in the simulation that I need to keep in mind. Okay. Paste table entry save. So what is the index here? Max. Okay. Save 31. Okay. This is the index 31 from the page 48. Okay. Yeah, there is mosquito. Something like this. Oh, that is why. Okay. Maybe something like this. Interesting. Okay, 0, 1, and then 2, and then 3, and 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Wait, is this correct? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20, okay, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, so the total is 32 here. Remember, we start from the index 0, right? Okay, so index 31 is actually this one. CE pipe, is that it? CE, okay, and then wait a minute. Rather than calling this PTA valid max, maybe we should call this just valid max, I guess. And then after that, this PTA valid shift become valid shift. Okay, yeah, it is not specific to page directory entry, if I understand correctly. Okay, valid max and then valid shift, basically checking whether this one is valid or not. Valid max, guess. Okay, it is valid. And then if it is valid, we try to get the page, I guess. Is from this one. Okay. 43. Let me check. Okay. Oh, page table entry. Okay, not that one. But this one, P5. Yeah, I'm trying to remember where we get this page 53. Okay. max VT is safe. Not that one. PFN max. Okay. So let's get this FN max and then get the page 53. Okay, and this only happen if it is valid. So if it is invalid, then yeah, we don't need to go further. Okay, valid, and then wait a minute. Using the PTA here, see 0xCA FN max. $78. Okay. $78. This one. I guess this is valid. Maybe. Translate, okay. Offset. Yeah, this one. Offset max and then get the offset. Okay. That make me wonder, should I put the maybe not. Yeah, I wonder if I should make it consistent, like putting the bracket like this. Maybe that is a good idea. Let me check. Yeah, something like this. Alright, yeah. Okay, let's do that. Okay, to make sure that this is one operation or something like that, or maybe distinguish is the better term. Wait a minute. Okay. Looks like I missed this one. Okay. Okay. 78. And then the virtual address here, offset max. The offset is 21. And 78. Now save page, and then adding the offset here, offset 21, 8. I think page speed is 5. Page speed at the offset 21. Okay, let's check this first. Okay. For this address, it is invalid. Okay, maybe we can put this on the new line, something like that. Maybe. trying to find the easier format to analyze here. Okay. Okay, it is invalid. This virtual trace, alright. And then for this one, the virtual trace 17F5, this one, oh, decimal 5. Okay, index 5, right? 212, or 0xt4, it is valid in the page 84. Okay, and then this one, the page table entry in the page 84. Okay, index 31, I guess. Yeah, decimal 31. The content is 0xe, which is valid on the page 78. Translate to this D5, it is the same, right, as this one. Okay, and get the value here. I'm still not sure if we can know the value from this memory term. Yeah, maybe not. So for now, my translation only stop until the physical trace, because I'm not sure how to get the value from those physical trace, at least from this information. Okay. Hello, the hangover. Welcome. Yes, got it. What you doing? Learning, I guess. Charlotte, what are you, bro? Is that even matter? Okay. We put on our socks. Welcome. Proceed. Yes, got text. Well, yeah, I just want to learn, and this is my learning process, I guess. Again, it is very subjective, and I'm not chasing speed here. want to understand what's going on. Okay, by myself if possible. Okay, interesting. Oh, the rest is page fault. Okay. Should I continue this? Or maybe trying another random output, or using the random seed here? Where is it? This one, I guess. Currently we are using the random seed 0. Yeah, I'm kind of curious, is there any chance where we get the fault in this page directory entry? I mean, from the script it looks like it is possible, like this one, but I'm not sure. Okay, wait, let me check the question here. Question: with a linear page table, you need a single register. With a linear page table, you need a single register to locate the page table. Assuming that hardware does the lookup upon a TLB miss, how many registers do you need to locate a two-level page table? A three-level table. Okay, with a linear page table, you need a single register to locate the page table. Assuming that the hardware does the lookup upon a TLB miss, how many registers do you need to locate a two-level page table? Register. A single register to locate the page table. If we have two-level page table, guess like this one. What is it called? I mean, maybe we can say this page directory is another form of the page table, and this page table entry is also the page table, another form of page table, or maybe not really the entry, I guess. So maybe this one is page table level 1, and this one is page table level 2. Maybe something like that. But yeah, how many registers we need to locate a two-level page table? Is it gonna be two register? I don't think so. Well, I guess instead of translating this, maybe we can take a look at the question. question 2, we're gonna do translation again, I guess. How many memory references are needed to perform its lookup? Okay. Given random set, okay. Yeah, maybe try answering this question first. And then, or maybe, yeah, let me plan for the next session. Okay. How many memory references are needed to perform its lookup? Given your understanding of how cache memory works, how do you think memory reference of the base table will behave in the case? Will they lead to lots of cache hits, and thus fast access? Okay, maybe. Yeah, we should take a look at the random seeds 1, I guess. Simulator with random seed 1, and then take a look at question 1, and then after that question 2, yeah, and so on. Question 3. Maybe this is the order, I guess. I mean, in the question 2, we will need to perform translation to check what is it called? How many memory reference are needed to perform its lookup? Okay. Alright, so next session we will take a look at the random seed 1, I guess. We will try the simulator with random seed 1, translating those, all of this, which probably a lot. How many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Translating this 10 virtual address. Okay, yeah, let's just start setting this 10. I mean, I guess we can shrink that with this -n flag. Let me try 3. Okay, 67. Is this still similar or okay, this is similar. Yeah, maybe let's take a look at this. Translating 10 is a lot. Let's sync that to 3. I mean, considering a lot of trouble just trying to understand one translation here. Okay, let's try the simulator with random seed 1, and 3 virtual address, and then after that take a look at question 1, question 2, and question 3. Basically this question. I'm not sure if I am able to do this on one session, so we will see how it goes, but this is the first task that we will check out on the next session. Okay, so I guess that's it for now. Thank you for watching and see you next time. Bye bye.